the movie begins. So there it is, we're recording now. So we're talking first here about chapter 12. And chapter 12 is all about sequences and series. And it's sequenced like I think there's a movie, Unfortunate Events, right? Sequence of something like that.
A series of unfortunate
A series,
events.
okay. So it should be a sequence because it's just a bunch of things. First thing happens, second things happen, third things happen, and a series. So like a sequence, we had the Fibonacci sequence, right? We talked about that last class, right? So 1, 1, 2. I'm just taking the previous terms and two previous terms and adding them to get the next term, right? And a series like E, right, is the series. So this is a Greek letter, capital S, sigma. It's sigma, right? So it's right. It's this guy. This is sigma. So it's the sum, and sigma means sum. We're adding up. So from I equals 1 to, let's say, n, right, of 1 over n factorial, and then let's add 1 to all of this, right? So now there's a couple things in there we don't understand yet, right? So, but first of all, this symbol is a Greek letter called sigma, like we use pi for about 3.14, right? So we use sigma when we say we want to add things up, right? So for example, the sum of 1 over 2 to the n, right, from n equals 1 to infinity. So that's 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed, right? You get the idea? Yes?
Professor?
Yes.
In that first example you showed,
Yes.
should that be 1 over I factorial? Or
yes, I factorial, yeah, because I used my index I. Thank you.
Yeah.
Yeah, and I'll explain this. This shouldn't make a lot of sense to you yet, but this one is a little bit easier, right? This is one half to the first power, 1/2 to the second power, 1/2 to the third power, right? So this is a series, right? So these two guys are series. So when I start to add things up, it's called a series. Okay. By the way, this sum is 1. And did I show that to you all last time? If I take a 1 by 1 square, right? So I got a square, 1 by 1 square, and I take half of it, right? And then half of it, so there's a fourth of it, and then half of that remainder piece, there's an eighth of it. So you can see I'm going to keep adding. I've got a 1 over 2 to the n here, 1/2 plus 1/4 plus 1/8, right? And you can see I'm going to eventually run out of room, and obviously the whole area adds up to 1, right? So I'm going to keep adding up all of those little pieces, so I'm going to get to 1. Right, and this is something called a geometric series. This is in 12.3. We're not doing that. You'll do it just in time in Calc 2. Okay, so the pieces that I'm taking out of this course to prepare you for Calc 1 will be taught to you just in time in Calc 2. And if they're not, you'll find someone on YouTube to teach it to you, or you'll come back and complain to me and I'll teach it to you real quick. So sequences and series, that's what we're talking about here. And the book is, because it's chapter 12 and they've already taught you chapter 2, they're using function notation. So I think the only thing kind of different about their notation is they'll say A of n is something like 1 over n factorial, okay? And I'm going to just say A sub n is 1 over n factorial. And so I'm using a subscript when I talk about it. They're using a function notation when the book talks about it, okay? Does that make sense at all, what I'm saying here?
Yeah.
So A of n is 1/2 to the nth power, right? So meaning a of 1 is 1/2. A of 2 is 1 over 2 squared. That's 1/4, right? So I'm just plugging in the values of n, right, as if it was an input of my function. And my notation is just going to be the first term is 1/2. The second term is 1/4. The third term is 1/8, right? So I'll talk about it using subscripts. The book will talk about it using functions, okay? But I'm pretty sure you've all seen functions before. But we're going to go in further depth with functions when we do chapter 2. And then most of the rest of the course is just talking about the different types of functions that you'll see in calculus. How are we doing here? Everybody okay? You comfortable? It's different, right? It's different, and I want it to feel different. I could start in chapter 2, but it's so boring just to start talking about lines right away. Y equals mx plus b, right? So just want to kind of shock you into we're at the next level here, right? By starting
Small
with
recap for me.
yeah, well, yeah, you suffered through a self-study there. Yeah, it's okay. All right, so in general, chapter 12 is sequences and series, all right? And so here we go, 12:1. And so in 12.1, and I invite you to read the book. It's not easy for students to learn to read a math textbook, but it's something that I would ask you to do, certainly for the rest of your mathematical careers. I'll suggest books for you to read as well. Like when you start taking calculus, you should get a Shaw's outline. Shaw's outlines. So for every course that you take, your science courses, your math courses, physics. Yeah, your physics, definitely I would do it for physics. It's every problem ever done, basically, and the proofs, all the proofs too. So, like when you take linear algebra, you want to get the Shaw's outline for linear algebra and the Shaw's outline for advanced linear algebra, right? So get both of them, and it's like every problem you'll ever have to solve, and so it's nice to have that. And the thing about those books is that it's stripped down. It's just problems. So, and that's how you want to read your textbook to start, is just look at the examples and start writing out the examples as they do them. And usually they'll skip steps, and your job is to say, oh, how did they get there? Oh, okay, I get it, right? So that's the way you start reading the book. Reading the book for us is not that easy, right? The reading the book for us, because of Math Excel, kind of, it sucks, really, honestly. Because you have to click on that part of the homework, and then you have to click on that section, and then you got to find the book, right? But if that's the case, I would say, go buy a used copy of the book, or go to the library and take photos of it and read it that way, if that's really annoying to you. So anyway, 12:1, and I've just lost my book. I have to open my book again, sorry. That's so annoying. If you're not active on the page, it closes. I can't stand Math Excel. When I'm in the class, I don't use the web homework. I have a feeling teachers like using the web homework because they don't have to grade anything. But I'd rather grade your homework than have web assigned or Math Excel grade it. Give me a second. I am recording all of this, so there's lots of dead time in my recordings. Okay, so 12.1 is it's just sequences, right? But I'm really going to be talking about series, uh, sequences and series, right? And what's the difference? Sequence is just my list of numbers, and the series is I'm adding all those numbers up, right? That's the easiest way to think of it. 1 second. So a nice thing for you to do would be read the textbook, right? And so, but we've got several objectives here. We want to be able to write out terms of the sequence, right? Or objectives. Right, so write out terms, and that means write out terms whether I'm adding them or not, right? Write out terms of a series or write out terms of a sequence, right? I don't do much with the recursive, so the book will talk about recursive sequences. I don't use those. We want to be able to find the nth term. Right, this is just what we're going to be doing today. We want to use the sigma notation. And that's really about it. So so Shalom's outline, by the way, right? You'll kind of remember that, I think. How am I going? Is anything too fast? Is everybody comfortable with the speed? This is pretty much my speed, right? But if I do start writing too fast, you just have to let me know, and then I'll slow down. If I have too much coffee, sometimes I'll write too fast, you know. So, but whenever I'm writing too fast, you let me know. Somebody, please. If you let me know when I'm writing too fast. The joke really helps if you participate a little bit. I'm writing too fast.
Oh my God, you're too fast.
Yeah, thank you for participating. Thank you. So let's look at an nth term, right? That's our first kind of idea here. So notation wise, I don't really like the way the book does it. I don't think I can help but write it the way they do. They'll use curly brackets for a sub n, right? And so they'll say, 1/2, 1/4, 1/8, and then ... So they're using that curly bracket for a set, right? A set of numbers separated by commas. And you'll have to, put that kind of notation into the Math Excel for answers. We'll look at some questions and answers today. And it's pretty clear what this nth term is, right? So a sub n here is what?
1/16. 1 over n.
Almost.
1 over n squared? Or 2n?
Almost.
Is it just n?
No. So this is my n is 1, right? This is my n is 2. So n is 1, n is 2, n is 3, right? Someone did it in the chat. 1 over 2. Yeah, 1/2 to what power?
N.
Yes, there it is. 1/2 to the right, or 1 over 2 to the n. That's the one I did before, right? 1/2 plus 1/4 plus 1/8. So sometimes you'll be able to find the nth term just by looking at it, right? Sometimes you'll be able to find the nth term just by looking at it. So for example, right, if I have the bracket b sub n, right, and I give you 1/2, 2/3, 3/4, ... Can you tell me what the nth term is?
4/5.
Yeah, the next one's 4/5, but what's the generalized term? How would you tell me what the
n over n plus 1?
n over n plus 1, right? So most of the time you can just figure out what the nth term is by looking at it, right? And so writing out an nth term, right, is just as easy as that. So if I give you a sub n is n minus 1 over n plus 1, right? So if I give you an nth term, could you write out my set for me? Anybody got the first number?
0.
Over 1.
Yeah, it's 1 minus 1 over 1 plus 1, right? Which is 0, yes. But I kind of, when I'm doing this at first, so 2 minus 1 over 2 plus 1, right? Yes, you with me? 3 minus 1 over 3 plus 1, dot, dot, dot. At that point, I'm hoping I could pick up the pattern pretty quickly. So what do I get? 0 over 2, comma, 1 over 2, 1 over 3, right? What is it? 2 over 4.
4.
Yeah. So
3 over 5.
yeah, etc. Right? And so I like to put them in, I like to do baby steps. I don't like to do all of this stuff in my head and then write down 0, right? I'd like to write out each term, using this, right? So n is 2, I'm plugging in 2 minus 1 over 2 plus 1, and then I'll do the calculation later, right? Try and do a baby step when you're doing these things at first, okay? So if I give you an nth term, it's easy to write out the sequence. If I give you a sequence, sometimes it's easy to give me the nth term. Sometimes it's not, right? But for us, most of our terms are going to be, most of our sequences are going to be arithmetic. Okay, so let me show you an arithmetic sequence. So how are we doing here? How are we doing here for speed for content?
Good speed for me.
Well, fine.
Good, good, thank you. And remember, you're paying me either directly or indirectly to teach you this stuff. So you don't want to be cheated, right? And we'll do things that are difficult this semester, but it's not that you can't handle it. You can. And like I said, when I'm lecturing, I'm trying to do things the way I think it's best to do them. But if you don't understand it, I can try and do it another way, right? So, so you just got to communicate with me, right? So arithmetic sequences, right? And series. So, for example, 1, 3, 5. What's next?
7.
Yeah, 7, 9. Right. It's pretty easy to see here, right? That I'm writing out the odd numbers. Yes.
Mm-hmm.
Yeah. And so the odd integers, odd positive integers, if you will. It's not so easy to write down this nth term just by looking at it. But we have learned how to do this in Algebra 1, right? So I'm picking n, and I'm picking a sub n. And I want to leave a space for my 0 term. So when we do these, we usually start at 1, right? It's just the way we learn to count, right? 1 apple, 2 apples, 3 apples. Computer scientists like to start at 0. And so we're often going to do things either starting at 0 or starting at 1. But I have already got, for 1, I had 1. For my first term, I had 1. For my second term, I had 3. For my third term, I had 5, right? And so you could already see I'm getting points on the line here, right? And obviously the slope is what?
Y equals x plus b.
Yeah, mx plus b. What is the value of m? What is the slope here?
2.
Yeah, it's 2, right? So I'm doing the y2 minus y1 over x2 minus x1. So I get 2 over 1, which is 2. No matter what 2 points I picked, if it's an arithmetic sequence, I'm going to get the same slope out of it. And then who can tell me what the b value is?
One.
N minus 1.
Minus one, right? So remember the b value is the y-intercept. It's when the x is 0, right? It's the height of the line when x is 0. So I can just do that by working my sum backward, right? So b is -1, and then there's my sequence. So a sub n is 2n minus 1, right? So when it's arithmetic, it's easy to find the sequence, right? When it's arithmetic, it's easy to find the sequence. Should we do another one?
Yes.
Yes. So what's really happening in an arithmetic sequence, right? This one was geometric. We had this one was geometric, right? I had what? 1/2, 1/4, 1/8, and you can tell. Am I adding the same thing there in the geometric? Am I adding the same thing? No. So in arithmetic, I'm adding the same thing, and in geometric, I'm multiplying the same to get the next term, right? So in my sequence here, I'm adding 2 to get the next term. And over here, I'm multiplying by 1/2 to get the next term. So arithmetic and geometric, right? And they have different properties for us when we're in the calculus. We'll be doing different things with different sequences. So I kind of, in general, right, an arithmetic sequence, and I'll do another one in a second. Arithmetic is a sub n is a plus the first term plus d, right? I'm sorry, no, that's not right. Don't tell me. Yes, don't tell me. It's n minus 1 times d, right? Where d, so a sub 1 is the first term, right? D is the common difference. Right, so if I took any two terms, 3 minus 1 is 2. 9 minus 7 is 2. So the common difference of consecutive terms, right, is that value of d. And so we want to really kind of think of this guy in that form, right? So we'll get to this one again. Now, does this one look like that? No.
Yes.
Well, yeah, kind of, right? Kind of.
You got the n minus 1
Yeah,
there. You got
right.
the d, bring that over. The plus first term is the only thing really out of place.
Yeah, so that's the question here is how can I make this look like this? Well, I can cheat, right? I already know that the first term is 1, and then what am I adding every time?
2.
2. So there's my d, right? And if you see now, if I distribute this 2, right, I get the 2n minus 1 again. So I can cheat on most of these. If I already have the whole sequence, I could just go into that formula, or I could think about it like an mx plus b, right? So, but we need this form of it for a certain type of problem that's coming up. Okay. And so you say to yourself, well, how am I going to remember all of this? I think that's the hard thing about the math classes, is that not anything we do is not difficult, but remembering what to do is often difficult, right? Like walking to California is difficult, right? But every step is quite simple, right? So it's that, it's that thing, especially if we get nervous on exams, right? Does anybody here ever blank out on an exam? Yeah. So
On about 90% of exams I've ever taken.
right. So we have a unique situation here in that, you know, how am I going to stop you from cheating on a test? It's not possible. So I just say, make a formula sheet. Right? So I'm going to allow you on your exams to have a formula sheet, 1 page front and back, and just cram everything you can on it. Right? So for example, you're going to have this formula for an arithmetic sequence on your formula sheet, right? And so this way, I don't have to look at you. I don't have to hear you looking through pages and pages of work. You got 1 page that you can just turn over. I don't have to care that you're looking away from the screen because you got, the unit circle pasted on your wall. I don't care, because I'm saying to you, just put it on 1 page so that you're organized and you practice that way. And so when you take the test, it takes out some of that kind of franticness, right? And so when you do the practice test, have your formula sheet there, and practice the practice test with the formula sheet, right? Does that make sense?
Yeah.
Angie, I'm sorry. What did you say there? I missed you 10 minutes ago. Was it for the other page? N is the numerator, not 1?
Yeah, that's okay.
Oh, you got
Yeah,
it. You got it now. Yeah,
yeah.
sorry about that. Sorry.
It's
I
okay.
just scrolled down in the chat and noticed that you had said something. Let's do another arithmetic, okay?
Professor, are
Yes.
you're recording this, right?
Yes. Can
Okay.
you see the bottom left of my screen? It's got a little pause button there, but you can see the timer.
I saw it. Okay.
Yeah, you see the
Okay.
timer going. Yeah. And I'm only recording the screen that I'm writing on. I'm not recording. I guess if I say your name, you'll hear your name in the recording. But I don't know why would anyone want to look at this if they weren't in our class anyway, right? So let's do another arithmetic sequence. Let's say 7, 3, -1, right? So it looks like what I'm subtracting 4 here. You agree?
Yeah.
So we could take the quick way out of this and say that a sub n is 7 plus an n minus 1 times that -4, right? So I'll put that in front. Minus 4, minus 4 times n minus 1. N minus 1 because I don't want to add to the first term, right? When n is 1, right? And 1 minus 1 is 0, so it kills it for the first term. And then when I add a -4 the first time, right? I only want to add 1 of them. So when I put the 2, is that making sense? When I put a 2 in, I get a 1 times a -4. When I put a 3 in, I get a 2 times a -4. So I'm adding that -4 twice. Is that making sense at all? What I'm saying there? And I can make that look a little bit better, right? I can do 7 minus 4n plus 4. So I get, 11 minus 4n. And that's the way we're used to looking at it, like an mx plus b, right? Pretty easy, right?
Very easy.
Is it okay if we do like 4n plus 11 or minus 4n plus
Yes,
11?
of course. And the whole idea, especially when you get into calculus, is you're just trying to write things. As a computer scientist, I understand this. Even as any scientist, you want to say as much as you can, writing as little as possible, right? Which is why we use all the notation in mathematics. We're trying to say as much as we can, writing as little as possible. So this one's preferred because I have 1 less sign, right? 1 less SIGN, right? I don't have to write the plus at the beginning. And for computer scientists, it's all about memory. We're trying to speed up our program. We're trying to write less code, that type of thing. And you'll see it in calculus a lot. And it's annoying. It's annoying that, I'm trying to, why do I have to, yeah, if 3 plus 4 is 7, why can't I just leave it as 3 plus 4? Why do I have to simplify it? It's the same idea. We want it to be said as quickly as possible, right? So what happens when we have to start adding these things up is the real question here, right? So we want to be able to find a sum. And so, for example, I'll have the sum of k equals 1 to n of k plus 4. And I might say write out the first 3 terms and the last term. So, and when you do this, you're kind of, you know, I mean, this one I could probably just type in the answer, but I want to kind of do things in baby steps, right? I want to be thinking like k plus 4 plus k plus 4 plus k plus 4, right? And then what the whole idea is, ... what is k the first time I do it, right? K is starting at 1, and then it's just counting, right? I'm just counting. It's an index, right? That's why I usually use I, because it's the index, right? The subscript, the first term, the second term. But they'll use any letter. So, but I'm putting in a 1 here, and then the index changes. So what's the first term? What's the next term? Well, I'm going to put a 2 in for k. And what's the next term? A 3 in for k. What's the last term I'm going to put in? That's up here. What's the last term I'm going to put in? N. Yes, so n plus 4. Right? So n plus 4. So that's, you know, that's about as abstract as it gets. But what if I did that same one for k equals 1 to 5 of k plus 4? And now I can actually find this sum, right? And the question is, can we find the sum easier? Is really the question. And the answer is yes, but let's do it the you know. So anyway, can I simplify this one?
35.
Well, yeah, I can go 5 plus 6 plus 7 plus ... n plus 4. And I think the computer will take either one of these. And I think I would rather you have this one, but you're going to write it out like this first, right? So think about it in terms of baby steps and then simplify if you can, right? Now this one, I can already see what my first 5 terms are, right? 5 plus 6 plus 7. What's next? It should be obvious, right?
8 and 9.
Yes. Plus 8 plus 9, and then we already got an answer, right? Did we already get an answer? 11.
35?
Yeah, 35, right? So it might be given to you abstractly. It might be given to you, you know, finitely, if that's even a word. But I might tell you only 5 terms, right? And then it's easy to find the sum this way. But the question becomes, can I find the sum a more elegant way? And the answer is yes. So we're going to have a few series that we want memorized, and that, of course, for you is going to mean I'm going to put them on my formula sheet, right? So these are our important series to memorize. So my first one is, the sum of a constant. So let's say the sum of C from I equals 1 to infinity. 1 to n, sorry.
Cn.
Yep. So this is c plus c plus c plus dot 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 n times. Right? And so, of course, that's going to be c times n, or nc. So this is what we want to memorize. We want to memorize the sum from I equal 1 to n of any constant is n times that constant. That's the thing we're going to memorize. Right? And that one really needs no proof, right? That's obvious, right? Do you agree?
Yes.
If I add up 5 n times, I get 5 times n, right? It's really obvious. I guess I could prove it to you, but the next one needs a little bit more proof. The sum from I equals 1 to n of I, which is, okay, so it's the first index, which is 1. Is everybody understanding that? The
Yep.
first value of I is 1. What's the second value of I? 2.
2.
And the next value of I is 3, plus all the way up to n. And this one is n times n plus 1 all over 2. This one needs a little proof, right? This one's a little bit strange. But again, what we want to memorize, what we want to put on our formula sheet, wink, wink, nudge, nudge. Don't tell anyone I'm giving you a formula sheet. They'll fire me. And if you want to get me fired, wait until you pass all the tests first, right?
It's fine. There are no snitches in this class.
That's right. So, I'm sorry. The sum of I is what I want here, right? The sum of I equals n times n plus 1 all over 2. So that's the second one I want to memorize. Wink, wink.
Oh, why is it over 2?
I'm going to prove it to you. Was that Alan?
Yes.
Yes, thank you. Yeah, so I'll prove it to you. Let's look at a couple sums first before I prove it, okay? Let's look at a couple of the sums. Let's say the sum from I equals 1 to 3 of I, right? That's 1 plus 2 plus 3, right? And that is 6, yes?
Yep.
Okay, let's see if that works for the formula. So the n is 3, right? So I got 3 times 3 plus 1 all over 2. That's 3 times 4 over 2. That's 12 over 2. That's 6. So it seems to be that's why it's over 2. But it's going to work for more than that, right? It's going to work for more than that. Let's see. The sum of I equals 1 to 10 of I. So 1 plus 2 plus 3 plus 4 plus 5.
55.
Yes, 6 plus, help me, what do I have to go up to? I have to go up to 10, right? 7, 8, 9, 10. Okay, well, that's the 10. That's a 10, right? That's a 10. There's 30, 40, 50, and I've left over 5, so 55. But of course, if I just put that 10 in the formula, 10 times 10 plus 1 all over 2, I get to 5 times 11, which is the 55. Yeah, yeah. So the formula seems to be working, right? So we'll prove it now. So I'm going to prove it the way that supposedly Frederick Gauss proved it when he was 7 years old or 8 years old. But then we're going to prove it another way in section 12.4, right? So this is the proof by Gauss. I'm going to say the sum is 1 plus 2 plus 3 plus ... all the way up to n, right? But I want to back up a couple of terms. So what's the previous term to n?
N minus 1.
N minus 1. Is everybody okay with that? Remember, Joe struggled through all this. This is why he's answering things quickly. He did all this on his own. I don't know when, Tuesday, all day Tuesday.
Yeah, yesterday I didn't want to do my English homework, so.
Oh yeah, I my desk is always clean when I don't want to do any homework. What comes before? Is everyone okay with the n-1? Right? I'm thinking of, so if my last term was 10, the term before it was 9, right?
Yes.
And the term before that was 8, right? So, but how would I say that? How would I say the n-2? So I'm gonna put an n-2 there, right? And then I'm gonna write that sum again, but I'm gonna write it backward, right? So that same sum is going to be n plus n-1 plus n-2 plus ... 3 plus 2 plus 1. Right? You can kind of see where I'm going here. And you know, I'm not a genius. Gauss was a genius. You know, I'm not a genius, but I can remember things, right? So you know, my teachers taught me how to do this stuff. That's what I'm doing to you. So it's not like I'm supposed to be able to figure this out, right? We kind of, in mathematics, once we learn something, we want to kind of adopt it and kind of steal it, right? But I'm going to add these things up. So on the left side, I get 2s, right? I get twice the sum. The sum plus the sum is 2s, right? And then look, notice what happens here. What do I get when I add these two up? I get an n+1. And when I add these two up, I also get n+1. In fact, when I add any of these terms up, I get an n+1 out of them, right? So I get an n+1 how many times?
N times.
N times, right? So n+1 plus ... n times, right? And so I see I get 2s equals n times n+1. And then, of course, if I divide by 2, right, I get the proof that the sum is n times n+1 all over 2.
That's a long process to get that proof.
Yes. But the proof isn't on your test. Okay. So the test will not include proofs. If I do include a proof, it would be an extra credit problem. Was that Angel who said that? No, I'm sorry. And thank you for having your camera on, Angel. It feels a little bit less lonely in this void.
Oh, I got you.
So proof, yeah, nice, Joe, thanks. So yeah, the proof is, I mean, it's tricky, right? But once you see it, you get it. It's not difficult. You'll see the way we're going to prove them. Hey, Diego, thank you. The way we'll prove them in 12.4 is a little bit more complicated. But again, those proofs, if I give you one on the test, it would be an extra credit problem, okay? So let's go back to that one problem we had here. We had the sum of k equals 1 to 5 of k plus 4, right? And I don't know if you can tell, but can't I just add up all the k's and then add up all the 4's, right? So this thing really can be split into two sums, from k equals 1 to 5 of k plus the sum of 4 from k equals 1 to 5, right? Is that making sense? If I'm adding up a sum, I can add up the pieces of the sum first and then put them all together, right? And so this one I already have a formula for, and this one I have a formula for, right? When I add up 4 5 times, what do I get? 4 plus 4 plus 4 plus, right? It's 20, yes? So this one is that 4 times 5. I'm using that formula. And then what's the other one? It's 5 times 5 plus 1 all over 2, right? I'm adding up k 5 times. So I'm using my formula for k, right? Is that making sense at all?
Yep.
Yep. So now I get what? I get 5 times 6 over 2 plus 20. Okay. Well, that's what, 15 plus 20. And remember, I had a sum of 35 before, right? So with these formulas, I can get these sums a lot quicker, right? That's the idea here. And by the way, this is a huge part of calculus. It's called integration, right? So if you've seen any calculus before, we're going to be taking derivatives of functions. That tells us the slope at a point, and then we're going to be taking integrals of derivatives, and that's going to give us area under the curve. And the way you find area, of course, is by adding things up, right? So we're going to see this summation notation again in Calc 1 and Calc 2, and etc. So so we have two more that we want to look at. Okay, two more of these important ones. Sorry, Grace, you said, could you repeat that last part? And you're asking me about the problem on the page, or what I was... Grace, what were you asking there? The problem on the page, yeah. Yeah, so let me do another one, right? Let me do another one, and we'll see. So the problem would be something like this. So I'll say find the sum, right? And I'll say I want the sum from I equals 1 to, let's just do 6 of 2n minus 1. Sorry, 2i minus 1, right? And so let's do it the simple way, right? Let's do it the simple way, the kind of childish way first. I want to put I in as 1 up to 6, right? So I like doing 2 times 1 minus 1 plus 2 times 2 minus 1 plus 2 times 3. And this is me thinking on paper as opposed to thinking in my head, right? But you see what's going on. I'm going to put a 1, a 2, a 3. I don't think I really need to keep changing colors here. You get the idea of what I'm doing, right? And you say, well, I don't need to do that. And I know you don't. I know you don't. You're smarter than that. But this is the way, when you're first doing these things, you want to write them out this way. And then I want to simplify everything, right? So what is this? 2 minus 1. And then what? 4 minus 1. You see what I'm... So it's kind of easy. I can see the pattern here now, right? Yes, you with me? And so then what do I get? I get a 1 and then a 3. And you kind of remember that we did this one. These are my odds, right? So it's the first 6 odd numbers, adding up the first 6 odd numbers, right? Remember, I got that pattern for the nth term of the odds. And now I'm just adding these up, right? So what do I get? 9, 18, 25, 36. Is that right? Can someone double check me there?
Yeah.
Yep.
36.
36.
Yes.
Now, Grace. So Grace was asking me, can you do that part again? So now let me do it the more sophisticated way, right? I know that the sum from I equals 1 to 6 of 2i minus 1 has got to be the sum of 2i minus the sum of 1, right? And I'm getting a little bit lazy here on my notation. I know I'm going from 1 to 6. I'm not going to keep writing it, right? But if I'm adding up 2 times something, can I add up to something and then multiply it by 2? Right? Does that make sense to everybody? So I'm going to say I can do the 2 times I minus the sum, right? 2 times the sum of I minus the sum of 1. And for each of these, I have a formula, right? Right? So remember, I have 2 formulas right now memorized. I've got the sum of C is n times C. The sum of I is n times n plus 1 all over 2. Right? I've got those 2 formulas memorized. Not really, they're on my formula sheet, right? So I'm going to do 2 times the n times n plus 1 over 2 plus 2 times n. Right? So remember, so I'm taking this part in green and substituting that, right? Does that make sense? I'm taking my known formula and putting it in for the summation, that notation I had. And notice that my notation has changed from the index I to the value of n. And what is my final value of n? It's 6. So I'm plugging in the 6 now. So 2 times 6 times 6 plus 1 all over 2 plus 2 times 6. And yes, of course, I'm being a little silly there. I know you can, you can simplify that a lot quicker, right? So that's 6 times 7 plus 12. Help me.
I don't think that's correct.
Aren't we supposed to subtract?
Subtract 12.
And I
yes.
don't.
So it
Oh,
would be minus 6.
Yeah, you're right. You're right. No,
Yeah,
no.
Minus 6 instead of minus 12.
Yeah, thank you. Oh my God, Robert, what's the matter with you? Don't worry, I'm recording it, so you've got proof. That's just n, right? The sum of 1 is n. Sorry. Now I've got it right, and it's minus. Sorry, I'm trying to. Grace is going, what the hell's going on? So now I'm right. Yes?
Yes.
So that's 42 minus 6, which is the 36 I got. Sorry about that. Grace, I screwed that up, but you okay there now?
Yes, thank you.
Okay, good. So the whole thing is making that. I mean, look at this. If I asked you to find the sum of the first 300 odd numbers, you're not going to do it this way, right?
Slight work.
Right. So that's what we want, right? We want the sum from I equals 1 to 300 of 2I minus 1, right? I don't want to do that that step-by-step way. I want to use my formulas. So I get 2 times the formula for the sum of I, that's n times
90,000.
Yeah, n plus 1 all over 2, minus n, right? And I'm putting in, and of course I can simplify this, right? I can cancel here. I get n squared plus n minus n, so I get just n squared, and then I'm plugging in 300. Yep. So that's a 9 and 4 zeros, right? 90,000. A lot easier that way, right? So we have a special sum, 4 of them, the special series that we want to memorize. Let me put them all on one page, okay? So here again are our special series. The sum of any constant from I equals 1 to n is n times that constant. So the sum of 5, right, a bunch of times would be 5 times n. The sum of the indices is n times n plus 1 all over 2. Let me try and be a little neater. And again, I'm going from I equals 1 to n every time. The sum of I equals 1 to n of I squared. So these are the indices squared, right? That's n times n plus 1 times 2n plus 1 all over 6. Joe, I can't believe you did all this by yourself.
I did. It was not fun, but it was better than English homework.
So these are the 4 we want to memorize. And I don't know if you see what's going on here. But we're basically having the ability to find the sums of what kind of objects. Can you see what's happening here, and why I would be possibly getting these sums? What am I going after here?
Building blocks of any given equation.
Yeah, that's a good way to think about it. Polynomials. So we're having x terms and x squared terms and x cubed terms. So we're trying to be able to find sums of polynomials. And for us in calculus, just don't write this. If I have some polynomial p of x, let's say from 1 to 3, I can get the area under that curve, right? The area is the integral from 1 to 3 of p of x. And it turns out to be the sum. It turns out to be the sum of the polynomials, the sum of the heights of that polynomial. And we're going to do it with this stuff that we learned in pre-cal, right? So let's take a look at a homework problem here.
So I do have one question.
Sure.
Would the formula for I to the fourth be just the formula for I squared squared?
Yeah, exactly.
Okay.
Yeah. We usually stop here.
Yeah,
After
because
at this
that's-
point, we kind of, we can figure
Yeah.
anything out after this one. Yeah. So let me look at a couple of homework problems here for you from 12. So this is homework 1. This will be the only homework
Oh, I have that.
that you have to do at this point. I'm almost out of time, so let me just share screen here. So you will have some of you will have different numbers in mind. So, but it's the basic idea. But can you come up with the nth term for me?
15.
Well, one. So you see, my numerators are 1 and 2 and 3. The numerator is n, right?
Yeah.
Everybody there? Okay. So wait,
Yeah.
I've got 1/3, right? Plus 1/3 plus 2/4 plus 3/5, and I'm trying to put that as a sum notation, right? From I equals 1 to whatever it had said. What did it say? Don't tell me.
15.
15, yeah. And so, but what's the nth term? Well, upstairs is just n, right? And what's
N over.
downstairs?
N plus 2.
M plus 2. So it will be something that you can just figure out, right? Usually by looking at it, right? I can think of that downstairs sequence. Is everybody okay with that? I don't want to slight you there, because some of you might not see it right away, but you can clearly see. I think everyone can clearly see that upstairs is just n, right? I'm saying what's if n is 1, what can I identify there, right? If n is 2, can I identify anything there? If n is 3, right? First term, second term, third term. Whether I use k or n or I, doesn't matter, right? But what if I didn't see downstairs was n plus 2? Well, it's at least it's arithmetic, right? First term, second term, third term, right? So remember I did a and a sub n, n and a sub n, and what's my slope is 1, right? And what's my b value? Well, what's next? 5 to 4, 4 to 3, 3 to 2, b is 2. So there it is. A sub n is 1 times n plus 2, or just n plus 2. So I can always go back to that linear piece that I had, right? Is that making sense? I think I went really fast there, but is everybody with me?
Yeah.
Thank you. Thank you, Paris. Alan, thank you. I got to take attendance real quick, so if you don't want your camera on right now, you can turn it off. I'm just going to take attendance like this. I love the new form of attendance. But how are we feeling? We're feeling okay about things? Let's look at another homework problem. So find the sum of this sequence. I can use I can add up 5 15 times.
Professor,
Yeah.
we can't see the homework problem.
Thank you. So find the sum, right? So I'm going to use my formula for this. It's just 5 times what? 15, right? This is the sum of 5 15 times. 5 plus 5 plus 5 15 times, so it's 5 times 15.
75.
Yeah. This is the sum of the first k indices, right? So 1 plus 2 all the way up to 40. Yep, so 40, right? So we okay here? Right, so the sum of I equals 1 to 40 of I. Well, we have a formula for that, right? We know that is n times n plus 1 all over 2 when n is 40, right? So 40 times 41 all over 2, or 20 times 41. Somebody help me. Do we get it? 820?
1,640
20 times
over 2, 820 would be the final
820.
answer.
820, yeah. Pretty easy, huh? So here's one with a new indice, and you see I've got a quadratic here, right? X squared plus 6. So in calculus we're talking about the area under the curve there. So from k equals 1 to 3 of k squared plus 6, right? So this is a homework problem, right? The sum of k equals 1 to 3 of k squared plus 6. Well, this one we could do the long way, right? In fact, it's pretty quick. 1 squared plus 6 plus 2 squared plus 6 plus 3 squared plus 6. Yes, you with me? Easy, right? So I get 1 plus 6 plus 4 plus 6 plus 9 plus 6, right? So I get 1 plus 4 plus 9 plus 3 times, there's 3 6s, right?
32.
Yeah. So I get 14 plus 18, 32. Okay, but let's do it the more sophisticated way. So we're saying that the sum of k squared plus 6 is the sum of k squared plus the sum of 6. Now I know my indices go from 1 to 3. I get a little lazy, and I don't mind you being lazy like this, right? We're kind of adopting that we know that the sum is from 1 to 6. I don't have to keep writing it every time.
1 to 3.
Yeah, 1 to 3. Thank you. So, and I know a formula for k squared. Well, I have it written down. N times n plus 1 times 2m plus 1 all over 6 plus 6 times n, right? Remember, the sum of 6 n times is going to be n times 6. But I know the value is n is 3, right? My last value is 3.
It's 14 plus 18.
Yes, thank you. So 3 times 3 plus 1 times 2 times 3 plus 1 all over 6 plus 6 times 3. So 3 times 4 times what, 7?
Yep.
12 over 6 is 2, so 14 plus 18 is same answer, 32. Right? I mean, they almost took the same amount of time doing it both ways, but when I ask you for the first 500 term, it's hideous to have to do it, term by term. I think that's typically all of the homework problems. They're all like that. That's the end of it. Yeah. Another one to look at. I'm out of time, so I can't do it. So that's good though. We don't care. So read the book, right? Read the